And the next topic is LCR circuit. See, in AC circuits, this LCR circuit plays very important role, because if you learn this LCR circuit, the total problems from this chapter you can solve it easily, because the total topic and total formulas are based on this concept only, and whatever the problem it is there from the AC circuits, you can solve it easily by using this LCR circuit. So that is the reason my circuit is considered as a very important question from this AC circuits chapter. Now we see each and everything from the LCR circuit. See, inductor, capacitor, resistor. If all are connected to AC source, this is the AC source. V is equal to V naught sin omega t. This is the inductor. This is the capacitor. And this is the resistor. Now, in an AC circuit, if the L, inductor, capacitor and resistor, if all are connected in series and connected to one AC source, then what is its RMS value? Then what is its impedance? And how can you find the phase difference between voltage and current? Then all those things we can learn from this circuit diagram. See here, this is the inductor, and potential across the capacitor is given by Q by C, and that is given by V is equal to IR, like this. Now, in the circuit diagram, inductor, capacitor and resistor, these three components are connected in series and connected to one AC supply. Now, the voltage applied by the source is given by V is equal to V naught sin omega t. Similarly, the current at any instant time is given by I is equal to I naught sin omega t plus phi. V is equal to V naught sin omega t, I is equal to I naught sin omega t plus phi. How much phase difference is there between voltage and current? Pi. Pi is the phase difference between voltage and current. Now, from this equation, the potential drop across inductor, capacitor and resistor is equal to the total potential which is applied by the source. How can you write that one? VL plus VC plus VR is equal to V. VL plus VC plus VR is equal to V. Next, the potential difference, potential drop across resistor. The potential drop across resistor is given by VR is equal to I into R. Similarly, the potential drop across inductor. The potential drop across inductor is given by VL is equal to I into XL. Similarly, the potential drop across capacitor. The potential drop across capacitor is given by VC is equal to I into XC. All of you followed? This is the instantaneous voltage. Instantaneous current. The total potential drop across inductor, capacitor, and resistor is equal to the total potential applied by the source. And the later, the potential drop across the resistor is given by this much, and potential drop across inductor is given by this much, and potential drop across the capacitor is given by this much. Now, all of us see the phasor diagram. In the phasor diagram, this part is represented by resistor, this part is represented by inductor, and this part is represented by capacitor. Now see, for resistor, the current value and voltage both are lying on the same line. So that is the reason for resistor there is no phase difference between voltage and current. So that is the reason all are lying on the same. Whereas inductor, here inductor, voltage is leading the current. Voltage is leading the current by how much angle? 90 degrees angle pi by 2. So that is the reason this is the voltage line and this is the current line. Whereas in case of capacitor, here current is leading the voltage. So that is the reason here it is represented by this much. Now see, in this one, OA is the vector for resistor where voltage and current both are in the same phase. OB is the line which is represented by inductor. Here voltage is leading the current, and OF is the line which is represented by capacitor where current leads the voltage. Now suppose here two cases will arise. Suppose if VL is greater than VC, what's happening? If VL is greater than VC, then the total circuit is inductive dominant circuit. In such a case, we have to write the equation, because if the VL is greater than VC, you have to write the resultant of these two can be represented as VL minus VC. Suppose if VC is greater than VL, in such a case you have to take this VC minus VL. In this way you have to take. This is so important. If the inductor is dominating the capacitor, the resultant of these two is VL minus VC. If the capacitor is dominating the inductor, you have to take VC minus VL. VC minus VL. Suppose for this question, suppose if I am taking VL is greater than VC, the resultant is given by VL minus VC. So the resultant of these two, VL and VC is VL minus VC is acting along the line OD. Acting along the line OD. Now this VL minus VC is acting in this line, VR is acting in this way, and the resultant of this VL minus VC and VR gives in this way. What is the line? It gives OH. Then OH gives the resultant of VD and VA. Now that thing we can find out by using that graph. See? Now see, in this graph I am taking this triangle. From the triangle OAH square is equal to OA square plus AH square. OH square is equal to OA square plus, in place of AH I can write OD. AH is equal to OD. What is the value of OH square? Its value is V square. OA square value VR square, and OD value VL minus VC whole square. Finally, if it is V, here you will get square root of VR square plus VL minus VC whole square. What about the VR value? The VR value is nothing but square root of VR square. VR square value is nothing but I square R square plus VL value I XL, VC value 1 by IC value I XC, whole square. From this, all these terms, if I am taking I is common, it will be V is equal to I into square root of R square plus XL minus XC whole square. Now, V by I is equal to square root of R square plus XL minus XC whole square. Like this also you can write R V by I is equal to square root of R square plus XL means it will be omega L, XC means 1 by omega C whole square. Now this in place of V by I, this term is equal to resistance, then total resistance is nothing but Z, and the Z is equal to R square plus omega L minus 1 by omega C whole square. And this we call it as a impedance of the circuit. This we call it as a impedance. What is the meaning of impedance? Impedance is nothing but the net opposition offered to the AC by inductor, capacitor and resistor. This total resistance we call it as a impedance. It is represented by the symbol Z, and Z is equal to square root of R square plus omega L minus 1 by omega C whole square. And from this one we can find the IRMS current. So VRMS is equal to IRMS into Z, and finally IRMS is equal to VRMS by Z. And what is the equation? VRMS by the Z equation, square root of R square plus omega L minus 1 by omega C whole square, and this gives the IRMS equation. IRMS equation. Once again, all of you see the terms, because if you want to know this question, the total derivation depends on this graph. What is this graph? See, first, once again, first I am taking three lines: resistor line, inductor line, capacitor line. Resistor, there is no phase difference. That is the reason all are lying on the same line. For inductor, voltage leads the current. How much angle? 90 degrees. For capacitor and this one, here current is leading the voltage, because this is the current line, this is the voltage lines. For capacitor, current is leading the voltage. For inductor, voltage is leading the current. But for resistor, both are lying on the same line. That is the reason there is no phase difference. Suppose if VL is greater than VC, the resultant is given by VL minus VC. This is represented by OD, and the resultant of this VL minus VC and VR, it is passing through like this. Here it is given by H, and I am finding the resultant of this value, OH value, by using parallel ruler. What is parallel ruler? I am taking the triangle OAH. The triangle OH square is equal to OA square plus AH square, and from this one OH value is V, OA value is VR square, and OD value VL minus VC whole square, and later the derivation follows. So V is equal to VR square, VL minus VC whole square, V is equal to I square R square, and VL value IXL, IXC, and later if it is I is taken out, it will be like this, and finally V by I is nothing but resistance. The total resistance we call it as the Z impedance. So Z is equal to R square plus omega L minus 1 by omega square whole square, and this Z is called impedance. And from that one, the RMS value of voltage is equal to RMS value of current and Z, and finally IRMS is equal to VRMS by square root of R square plus omega L minus 1 by omega square omega C whole square. Now, how can you find the phase difference between voltage and current for this LCR circuit? See, this is the phase difference, pi. Then from the diagram, tan pi is equal to AH by OA, tan pi is equal to AH plus I can write OD by OA. OD value VL minus VC by OA value VR. And as here I can use IXL, IXC by IR. I cancel. So finally XL minus XC by R. So tan pi is equal to XL minus XC by R, or pi is equal to tan inverse XL minus XC by R. XL minus XC by R. So this is the phase difference. This is the phase difference between voltage and current. This is the phase difference between voltage and current of LCR circuit. Now I will discuss one special case. Suppose in this diagram, if VC is greater than VL, what happens? So far in the diagram we learned VL is greater than VC. Suppose if the VC is greater than VL, VC minus VL, the resultant is passing through in this way, and we have to apply all this law like this. By the same method, everything you have to apply like this. Then how the equation change? See, IRMS is equal to VRMS by square root of R square plus 1 by omega C minus omega L whole square. In the previous equation, omega L minus 1 by omega C whole square, because this is dominating the capacitance. But now capacitance is dominating the inductance. In such a case, the equation will be like this. And for similarly, the phase angle also we have to take tan pi is equal to XL minus XC. It is not like that. It will be XC minus XL by R. Like this you have to take. The only difference is whether it is a capacitive dominant circuit or inductive dominant circuit. If it is a capacitive dominant, XC minus XL, then 1 by omega C minus omega L. If it is an inductive dominant circuit, then you have to take XL minus XC by R, or omega L minus 1 by omega C whole square. That is the only difference. So you have to check whether it is inductive dominant circuit or capacitive dominant circuit. So based on that only we have to solve the equation. Next, resonant frequency. See, in LCR circuit, what we call it as a resonant frequency. Inductor, capacitor, resistor, all are connected to AC source. Inductance, capacitance and resistance. Then what is the meaning of resonant frequency? See, here I am writing one term. IRMS is equal to VRMS by square root of R square plus XL minus XC whole square. Now, in this particular equation, or if I am writing like this, IRMS is equal to VRMS by square root of R square plus omega L minus 1 by omega C whole square. Now, what is the meaning of resonant frequency? If the frequency is varying at particular frequency, If XL, XC, if both are equal, it's a condition the impedance is minimum and current is maximum. Such a frequency we call it as a resonance frequency. If we are observing the maximum current in the circuit, when it is possible, if the resistance is minimum, if the impedance is minimum, when you get the impedance minimum, if the XL and XC, if the both the values are equal, then it is possible to get impedance is minimum. If the impedance is minimum, automatically current in the circuit will be maximum. Such a condition we call it as a resonance frequency condition. What is the condition? At that condition, XL, XC both are equal. What is the XL value? Omega naught L. What is the XC value? Omega naught C. If I am cross multiplying, omega naught square is equal to 1 by LC and omega naught is equal to 1 by square root of LC. And finally here also you can write 2 pi N naught is equal to 1 by square root of LC, and finally N naught is equal to 1 by 2 pi into square root of LC, and this frequency we call it as a resonant frequency. Once again, all of you try to understand the meaning of resonant frequency and the equation for resonant frequency. If the frequency is varying at particular frequency, XL and XC values are equal. At that condition, in LC circuit, impedance is minimum, current is maximum. If the impedance is minimum, current is maximum, that condition we call it as a resonant frequency condition. There, XL value, XC value both are equal. XL you can use as a omega L, XC I can use as a omega naught C. If I am cross multiplying, omega naught square is equal to 1 by LC and omega naught is equal to 1 by square root of LC. I can write omega naught is equal to 2 by N naught and 1 by square root of LC, and finally N naught is equal to 1 by 2 pi into square root of LC. See?